In this video, I'm planning on solving two example problems that require a mass balance to solve. And I derived the mass balance in a previous video, so if you want to see how the equations we're going to be using in this video were derived, go back and watch the video on the derivation of the mass balance. So let's just read through this problem, and we're going to follow the so I'm going to follow the steps that I'm going to use to solve all of these problems. So the first step is to just read the problem and make sure that you understand what's happening. So this says that we have a steady flow compressor. Oh, and first I want to mention that both of the problems I'm solving came from the 8th edition of Thermodynamics and Engineering Approach, the CBK, and they're from the 8th edition. These problems are also in the 9th and probably some earlier editions as well, but they're just going to be a different problem number. Okay, so this says we have a steady flow compressor, and it's used to compress helium from 15 psi absolute and 70 degrees Fahrenheit at the inlet to 200 psi absolute and 600 degrees Fahrenheit at the outlet. And then it says it gives us the outlet area and velocity and the inlet velocity, and it wants us to determine the mass flow rate and the inlet area. So basically, we just have a compressor. I mean, this problem is pretty straightforward. So we just have a compressor, fluids flowing in and flowing out, and it's being compressed. So let's draw a diagram. So this is our compressor. This is our inlet. I'm just going to call it 1. And this is our outlet. So this is just 2. So now let's start writing down the information that we know, and we also want to write down what we don't know and specify what we're looking for. So we have a steady flow compressor, and we're compressing helium from 15 psi. That means that P1 is 15 psi absolute. T1 is 70 degrees Fahrenheit. And I'm just going to convert this to Rankine. So 70 degrees Fahrenheit is 529.7 Rankine. And then P2, so it says the outlet, well actually so at the inlet 2, and then at the outlet P2, so P2 is 200 psi absolute. T2 is 600 degrees Fahrenheit, which is 1059.7 Rankine. And then it also tells us the outlet area and velocity. So the outlet area is 0.01 feet squared. The outlet velocity is 100 feet per second. And then it tells us the inlet velocity, so V1 is 50 feet per second. And then it wants us to determine the mass flow rate and the inlet area. So I'm going to put A1 is equal to question mark. So one thing that we want to look at, let's just list some assumptions right now. So it tells us that this is a steady flow problem. So what that means, what the steady flow means, is that the mass inside the control volume, or inside, so we should specify that this is our control volume. So the mass inside the control volume isn't changing with time. So basically this dm cv dt is equal to 0. And what that means is that the mass flowing into the control volume has to be the same as the mass flowing out. So basically M1, so the mass flow rate flowing in is equal to the mass flow rate flowing out. So this is just equal to the mass flow rate, and that's the other thing that we're looking for. I want to mention this steady state. So this problem tells us that this is a steady flow compressor. It might not always tell you that in the problem, even though you're going to need to make that assumption to solve the problem. So for instance, if you have you could have an engine or a pump or a pipe, and if you assume that it's been operating for a while, so basically it's not in the startup or shutdown phase, you basically need to assume that it's steady flow. And the reason why is because, well, let's consider a pipe. Like, if we have a pipe and we have fluid flowing through the pipe, when we first turn on the flow to that pipe, the mass is going to be changing in the pipe with time as it fills up with whatever the fluid is. But after a certain amount of time, the mass flow into the pipe has to equal the mass flow out. Otherwise, the mass in the pipe will keep increasing until the pipe explodes. So basically, if you have like with a pipe, if it's not telling you that it's a startup phase or a shutdown process, then you can basically just assume that it's steady flow, and that means that the mass flow rate in is equal to the mass flow rate out. This is the case with a lot of engineering devices. So in this case, we have a compressor. If this didn't tell us that the compressor was steady flow, we could pretty much just assume that for this problem, because we can't have, assuming that the compressor hasn't just been turned on, like it's assuming it's been operating for a while, if we have more mass flowing into the compressor than what's flowing out over time, the compressor is eventually going to explode because it can only, so basically we need to assume that the mass flow rate in is equal to the mass flow rate out. So I just wanted to mention that this problem tells us that it's steady flow, but it might not always tell you, and you might need to just figure that out based on the information given in the problem. Okay, so now let's also consider another. So we don't know, so we have helium, and I'm going to specify that this is helium. It's flowing into a compressor, being compressed, flowing out, and we don't know if this is an ideal gas or not. So I'm going to get some information. First of all, if we look up the critical temperature and pressure, and this is table A-1, and you're going to want to look at A-1E because we're using English units. So the critical temperature is 9.5 Rankine. The critical pressure is 33.2 psi absolute. Basically, we have a really high temperature at both the inlet and the outlet compared to the critical temperature. So just from that, we can probably assume that this is an ideal gas. The only thing that I'm also considering is that the pressure at the inlet is pretty low compared to the critical pressure, but the pressure at the outlet is pretty high compared to the critical pressure. The temperature is still extremely high compared to the critical temperature. So just from the temperature alone, I think that assuming ideal gas is a pretty good assumption. Although with that said, we don't actually have data for helium at these temperatures and pressures, and so we don't really, even if this weren't an ideal gas, we don't really have a choice. We need to assume it's an ideal gas in order to solve the problem. So in this case, I think it's a pretty good assumption that it's ideal gas just because the temperature is so high. But if, let's say, the temperature were lower, and then it might be a little more questionable as to whether or not it's an ideal gas. If you don't have the data available to calculate, well, you could use the compressibility chart, but if you don't have data available data available to make your calculations with a non-ideal gas, a lot of times you're just going to have to assume that you have an ideal gas in order to solve the problem. So that's something that you'll take into account sometimes. All right, so we have our problem drawing, our information, some assumptions. Now let's write down the equations that we're going to be solving. And so we already have one of the equations just from our assumption. So since we've assumed steady flow, we know that our mass balance is just M in, well, basically M1 is equal to M2. So this is equal to so the mass flow rate is equal to the area multiplied by the velocity divided by the specific volume. And then, so that's the mass flow rate at the inlet. The mass flow rate at the outlet is A2 multiplied by the velocity at 2 multiplied by the specific volume at the outlet. And this is equal to m dot. So what we want to find is the mass flow rate. And if we look at, let's look at the outlet. So we know what the area at the outlet is. We know the velocity. And we know that it's an ideal gas, so we can calculate the specific volume. So basically, we're going to use the ideal gas law. So PV is equal to RT. So then the specific volume is equal to RT2 over P2. So I'm just going to take this whole quantity, plug it into this equation for the specific volume. So then the mass flow rate is equal to A2, the velocity at the outlet, P2, and then RT2. So we know everything here. We know the area because it was given. We know the velocity because it was given. We know the pressure because it was given. We know the temperature, and we can look up the gas constant. So we know everything that we need to calculate the mass flow rate. And then if we look at the other thing that we want to calculate the area of the inlet. And we know that this quantity is just equal to this mass flow rate. Well, we know the velocity at the inlet because it was given, and we can calculate the specific volume from the ideal gas law. So basically we have everything we need now to solve this problem. And so I'm just, now we're ready to do the calculations. So let's do the calculations. And I'm going to look up R. We need the gas constant. So you're just going to get this off the table A-1. It's the same table that you got the critical temperature and pressure from. So this is equal to 2.6809 psi absolute, foot cubed, pound mass, Rankine. And one thing that I want to point out with this gas constant is if you look at that table, there's actually two different gas constants given. If you look at the units, they have different units. So you're just going to pick the one that has the units you're using. We're using pressure absolute, feet, pound mass, and I converted the temperatures from Fahrenheit to Rankine, so this is the gas constant that we want to use. Okay, so now let's solve for the mass flow rate. So the mass flow rate is equal to, we already wrote this equation for it, so A2, the velocity at 2, P2 over RT2. So now we can just start plugging in some numbers. So this is equal to 0.01 feet squared multiplied by 100 feet per second multiplied by 200 psi absolute divided by 2.6809 psi absolute foot cube pound mass Rankine, and then our temperature is 1059.7 Rankine. All right, now let's make sure our units cancel out correctly. We're looking for a mass flow rate, so we want units of pound mass per second. So the feet cancel, Rankine cancels, the psi absolute cancels, and we're left with pound mass per second. So this works out to 0.0704 pound mass per second. So this is our mass flow rate. And one thing I want to point out is a couple things. First of all, you want to make sure that you're using pressure absolute. And the reason why is because we have pressure absolute in our gas constant. So if we just had psi, if it just said psi, you'll need to determine if it's gauge or absolute pressure. But you might have psi gauge, like let's say that a lot of these pressure measurements are done with a gauge, and so you're going to get gauge pressure. So if you have gauge pressure, you need to add the atmospheric pressure to the gauge pressure to get absolute pressure. So make sure that you're using the correct pressure for the pressure, and then make sure that you're using the absolute temperature, so either Rankine or Kelvin in the case of SI when you're doing calculations that involve the gas constant. And then when you do your calculation, put all of your units into the calculations. The reason why you want to do that is because then you can make sure that all of your units cancel out correctly. If you go through this calculation and your units don't cancel out correctly, you know that you did something wrong when you derive the equation that you're using, and so then you can go back and check it and figure out what you did wrong. So basically with this, we know that we need a mass flow rate. So if after all of your units cancel out, you don't get units for a mass flow rate, you know you did something wrong, so you need to double check your equation. So putting all of the units in is a really helpful way to check your work and make sure that you did things correctly. All right, so we have the mass flow rate. Now the second thing we needed to calculate was the area of the inlet. So we know that the mass flow rate is equal to the area of the inlet multiplied by the velocity at the inlet multiplied by the specific volume. We're going to calculate the specific volume from the ideal gas law. So V1 is equal to RT1 over P1. And I'm just going to plug this directly into this equation like I did before. And then I get that the mass flow rate is equal to A1 V1 P1 over RT1. We're looking for A1, so let's solve for A1. So A1 is equal to m dot RT1 over the velocity at 1 P1. All right, so we know the pressure, we know the velocity, we know the temperature. So let's double check. Go back up here to the problem statement. So yeah, we have the pressure, temperature, velocity. And we know the mass flow rate because we just calculated it, and we know the gas constant because we looked it up. So we have everything we need to solve this problem. So let's go ahead and plug in our numbers, and we're going to put in the units as well. So 0.0704 pound mass per second multiplied by The gas constant is 2.6809 psi absolute foot cube pound mass Rankine multiplied by 529.7 Rankine, so the temperature. And then this is over 50 feet per second multiplied by 15 psi absolute. And again, make sure that you're using absolute pressure and not gauge pressure. So let's make sure all of our units cancel out correctly. Since we're looking for an area and our length units are in feet, we're going to want feet squared. So the psi absolute cancels, the pound mass cancels, this foot cancels, so we have foot squared, the seconds cancel, and Rankine cancels. So we're left with feet squared, so we're getting the correct units. So this is equal to, this is A1. A1 is equal to 0.133 feet squared. All right, so the last thing we want to do is make sure that these numbers, these values that we calculated make sense for the problem. We've already verified that the units came out correctly, so that's one clue that we probably did it right. But let's also check the values that we got. So for the inlet, we got 0.133 feet squared. The outlet is 0.01 feet squared, so that's probably a reasonable area. And then the mass flow rate, we got 0.0704 pound mass per second, which is probably a reasonable mass flow rate. If we had have calculated something like 100 feet squared for, say, the area of the inlet, you know that you probably did something wrong. You might have a number that's off by a factor of 10. So just check and make sure that the answer you're getting is reasonable for what you're solving for. Same thing with the mass flow rate. If you had have calculated, say, 100 pound mass per second, that's probably not very reasonable. So you would want to go back and check double check your calculations. All right, this is the second problem I'm doing, and this is number 5-13 from the same book. So this is Thermodynamics and Engineering Approach, CBK, and it's the 8th edition. This problem, I'm pretty sure this problem is also in the 9th edition, and it's also probably in earlier editions. It's just going to be a different number. So let's go through our steps. The first thing we're going to do is read the problem and make sure that we know what it's asking for, and then we're going to go through and set up our problem, determine our assumptions, equations, and then we're going to do our calculations. So it says a pump increases the water pressure from 100 kilopascal at the inlet to 900 kilopascal at the outlet. Water enters the pump at 15 degrees Celsius through, and then it tells us the diameter of the opening, and exits through, and then it tells us the diameter of the opening. We want to determine the velocity of the water at the inlet and outlet when the mass flow rate through the pump is 0.5 kilograms per second. And then it has a question about, will these velocities change significantly if the inlet temperature is raised to 40 degrees Celsius. So basically we just have a pump. So a pump is increasing the pressure of the water. So that's basically what we have. And we want to determine the inlet and outlet velocities of the water. So let's draw our pump. So this is our pump. This is the inlet and the outlet, and I'm just going to call this 2 and 1. And let's just start writing down some of our information. So it says the pump increases the pressure from 100 kilopascal to 900 kilopascal. That means that P1 is equal to 100 kilopascal and P2 is equal to 900 kilopascal. And the water enters the pump at 15 degrees Celsius. So T1 is equal to 15 degrees Celsius through a 1 centimeter diameter opening. So just make sure that it's clear. This is giving us the diameter, not the area. So the diameter is 1 centimeter. And the diameter at the outlet is 1.5 centimeter. And I'm just going to write these as meters right away because we know that we're going to need them in meters. So this is 0.015 meters, and this one is 0.01 meters. And we want to determine the velocity of the water at the inlet and outlet. So V2 is question mark, V1 question mark. And then it tells us that the mass flow rate through the pump is 0.5 kilograms per second. So basically, we have an assumption now. So our assumption is that we have steady flow. And the reason why is because it's telling us that the mass flow rate through the pump is 0.5 kilograms per second. We have a pump, and we're assuming that it's been operating for a while, so it's not in the startup, and we're also assuming it's not in the shutdown phase. So if it's been operating for a while, we know that the mass in has to equal the mass out, and the mass in the pump, so the mass in the control volume, and just draw this as our control volume. So the change in mass in the control volume with time has to be equal 0 because there's only a limited amount of space in the pump. We can't be adding mass. Basically, the pump wouldn't operate correctly if we were if the mass was increasing with time or decreasing with time. So the mass in is equal to the mass out, which is equal to the mass flow rate, which is given. So it doesn't specifically tell us that it's steady flow, but we can make that assumption based on the information that we're given. The other thing is, so we're given the temperature of the pump at the inlet. We're not given the temperature at the outlet, but I'm going to make an assumption that the temperature, so basically there's nothing in the problem saying that heat is being added to the pump or being lost. So if we assume that this pump is frictionless, we can assume that T2 is approximately equal to T1. In reality, T2 is going to be slightly higher than T1 because of friction effects and other things. But if we assume that it's frictionless, we can assume that T2 is approximately equal to T1. And with that assumption, we can assume that the specific volume is the same at the inlet and outlet. So specific volume is the same at inlet and outlet. So the reason why we can make this assumption is because let's figure out what phase our water is in. So we have H2O, and if we look at the inlet, it tells us that the temperature of the water is 15 degrees Celsius and the pressure is 100 kilopascals. Well, if we look up psat at 15 degrees, so psat at 15 degrees Celsius is equal to 1.7057 kilopascals. So basically our pressure is a lot higher than psat, so that means that we have a compressed liquid. So we have a compressed liquid at the inlet, but then if we assume that the temperature at the outlet is approximately the same as the temperature at the inlet, but then the pressure is even higher, that means that we also have to have a compressed liquid at the outlet. So we also have a compressed liquid at the outlet. Now, as far as the specific volumes being the same, if we actually had a table that we could look up the compressed liquid at the pressure and temperature, then they probably would be slightly different in reality. But the problem is we don't have data available for compressed liquid water at this temperature and pressure. And so we're going to assume that the specific volume is the specific volume of the saturated liquid. So we're going to say at the inlet, so we know at the inlet T1 is equal to 15 degrees Celsius, and we know that it's a compressed liquid. So we're going to say that the specific volume is equal to the specific volume of a saturated liquid at 15 degrees Celsius, which is equal to 0.001001 meters cubed per kilogram. Now, if we look at the outlet, we basically have the same condition with this assumption that we're assuming it's a saturated liquid, because at the outlet, since we've assumed that the temperature is the same, so T2 is 15 degrees Celsius, it's also, so it's going to be a compressed liquid. We don't actually have a table available with the compressed liquid, so we're going to assume that V2 is the saturated liquid at 15 degrees Celsius, which is equal to the same thing, so 0.001001 meters cubed per kilogram. So this is why we can assume that the specific volume is the same at the inlet and the outlet. And then while I'm looking at the data, we also wanted, so the second part of the problem says, will these velocities change significantly if the inlet temperature is raised to 40 degrees Celsius? So I'm going to also get the data at the inlet for 40 degrees Celsius. So inlet, if T1 is 40 degrees Celsius, it's still a compressed liquid. So we're going to get, so V1 is going to be the saturated liquid at 40 degrees Celsius, which is equal to 0.001008 meters cubed per kilogram. And then this is going to be the same at the specific volume at state 2. So now, so I kind of did this out of order. Normally we would get our properties after we've written down the equations we're going to use, but I wanted to go through why we're making the assumption that the specific volume is the same at the inlet and the outlet. So now let's write down the equations we're going to need. Basically, we're just going to need a mass balance. We've already kind of done that in our assumptions. So since we've assumed steady flow, we've said that the mass in the control volume isn't changing with time. So we know that the mass in is equal to the mass out. So m dot 1 is equal to m dot 2. And then we know that the mass flow rate is just equal to the velocity multiplied by the area over the specific volume. So we just set these equal. And this is equal to m dot, which was given. So now let's look at what we need and what we have. what we're calculating are the velocities. And we know, so if we look at, let's go look at what we have. So we know for our inlet, we know the pressure, the temperature, the diameter, so we can calculate the area from the diameter. And at state 2, we know the pressure, temperature, diameter, and we know the mass flow rate. So let's go back down and look at these equations. So we can basically solve, let's just start with V1, or the velocity at the inlet. So the mass flow rate is equal to VA V1, and we know the mass flow rate because it was given. We know the area because we can calculate it from the diameter, and we know the specific volume because we looked it up. So we can solve for the velocity is equal to m dot the specific volume over the area. So this is equal to 0.5 kilograms per second multiplied by 0.001001 meters cubed per kilogram divided by, and then the area. So I just calculated the areas. You could also plug the equation for the area directly into the equation that you're solving, but I just calculated the area. So the area for 1 is equal to 0.00079 meters squared, and A2 is equal to 0.000177 meters squared. So we can go put that into our equation. So A1 is 0.0007, actually this is 4 zeros. Probably better to write this in scientific notation, but 79 meters squared. All right, so let's make sure everything cancels out correctly. Since we're looking for a velocity, we're going to want meters per second. So the kilograms cancel, that cancels, and we're left with meters per second. So this is correct. So the velocity at the inlet is equal to 6.36 meters per second. And that looks like a pretty reasonable number to me. If I had have ended up with like 600 meters per second or 1,000 meters per second or something really huge, I'd probably question it. Also, if I ended up with something really small, like maybe 0.0008 meters per second or just something really small, I'd probably question that as well. But this looks pretty reasonable to me. So now we can calculate the velocity at the outlet. So V2 is equal to, and let's just write this out. So m dot is equal to V2, A2, V2. We know, so we're looking, well, actually, we're looking for the velocity. So let's solve this equation for V2. Rewrite that. So V2 is equal to m dot, the specific volume over the area. So basically the same thing we just solved for the velocity at the inlet. So this is equal to, the mass flow rate is still the same, so 0.5 kilograms per second. The specific volume is still the same, so 0.001001 meters cubed per kilogram divided by, and then we have a different area. So this area is 0.000177 meters squared. All of our units should cancel out the same as before because we're basically solving the same equation with different numbers. So this is equal to 2.83 meters per second. All right, so now so the second part of the problem was, if we go back up to the problem, it was, will these velocities change significantly if the inlet temperature is raised by 40 degrees Celsius? So what I'm going to do is recalculate the velocity at the inlet using, like, assuming that the temperature is 40 degrees Celsius, and that's going to change the specific volume. So V1 at 40 degrees Celsius is equal to, and then this is still the mass flow rate multiplied by the specific volume multiplied by the area. So this is 0.5 kilograms per second multiplied by, and then the specific volume is different this time, so this time it's 0.001008 meters cubed per kilogram divided by 0.000079 meters squared. It's all going to cancel out the same as it did before. So then the specific volume at the inlet, or sorry, the velocity at the inlet is equal to 6.38 meters per second. So if we compare that to what we got before, we got 6.36 meters per second before, now we got 6.38. So that's a pretty small difference. So the answer to the question is that I would say that the velocity does not change significantly if the inlet temperature is raised to 40 degrees Celsius.